The objective of this video is to frame our course approach within the context of AC machine systems. We're going to be setting the narrative up for what it means to analyze a motor versus what it means to design a motor. And in order to do this, we need to introduce the active components of electrical machines. So let's begin by talking about the broader components of an electric motor system. And to be clear about this, when we say motor system, we simply refer to a system of components that can create torque. And if this torque happens to be in the same direction as our shaft is rotating, it's an electric motor. If the torque is in the opposite direction of our shaft's rotation, it's an electric generator. So this discussion of an electric motor system applies to both motors and generators. So moving left to right, we start with either a power source or a power sink. Another way to say this is that if it's a motor, we have a power source that's used to drive our motor, and if this is a generator, we have a power sink or a load. And this power source could be the power grid, or it could be perhaps a battery, like in an electric vehicle. And depending on the power level of our motor system, this may be a single phase or a three-phase source. For this diagram, we're assuming it's a three-phase source. And in most modern motor systems, your power source is connected to a set of electronic circuits that act as a frequency converter to enable the motor to operate at variable speeds. And we'll abbreviate this as variable speed drive. That variable speed drive then connects to our actual electric machine. And the machine is rotating a shaft. It creates a torque upon a shaft, and that shaft connects to a mechanical load. In general, that load could be anything. It may be a compressor, it could be a pump, it could be an electric vehicle transmission, or if this is a generator, it would connect it to the prime mover, and that would be perhaps an electric engine, or an internal combustion engine, or it could be a jet engine. The point is that if it's a generator, it's connected to something that is creating mechanical torque on the shaft that the motor then converts to electric power. So we can divide this up as consisting of our power source or load, and we can lump our variable speed drive in here, and consisting of our electric machine. So if this is a motor, power is flowing this way, and if it's a generator, power is flowing this way. In some cases, you won't have the variable speed drive. The motor will be connected directly to the power grid. This, for example, is done with a line-fed induction motor. But in a lot of cases these days, we put a variable speed motor drive on there because it allows us to get higher efficiency and better performance, more precise control of our shaft. So from the motor drive's perspective, from this box's perspective, the source, our motor looks like an equivalent circuit. We can model it with resistances, with inductances, and with a voltage source. The voltage source is our back EMF. And from the motor's perspective, our power source or load looks like a multi-phase voltage source. So if it's a three-phase system, it looks like a three-phase voltage source. Phase A, B, and C, or phase U, V, and W, depending on convention that you are using. These voltages will have a certain magnitude and a certain phase angle. And similarly, the current will have a certain magnitude and a certain phase angle. And so we can say in these clouds, these are the equivalent models of each component in the system. For the motor, this is an equivalent circuit. And for the power source, this is an equivalent set of sources at a given frequency with a given magnitude and phase angle. And so your other coursework will teach you about the electronics to implement this and about the control algorithms that you need to implement in order to operate your motor. What this course is focused on is the actual electromagnetic design of this component, the motor/generator. So with this in mind, let's move to the next part of this lecture, which is an outline of the active components within AC machines. So I'm going to sketch here a generic 2D cross-section of a motor. That is, I'm going to show you the stator lamination and the rotor cross-section. And again, please pardon my drawing skills. So I've sketched this hypothetical drawing as a stator with some geometry, some stator teeth. And so this is our stator out here. This is the stationary portion of our motor that's presumably mounted within some kind of frame that secures it and prevents it from rotating. And inside here, we've got our rotor, and this is the portion of the motor that rotates. And at the very center of the rotor is the shaft. So what is not drawn on here are any of the components that are not used for active electromechanical energy conversion. All of these components are strictly magnetic components, that is, that they carry the magnetic field, and they are used in the process of converting electric energy to mechanical torque. And we're now going to break down the stator and the rotor separately in a series of diagrams. But remember that the complete motor system also includes the bearings, the frame, more details on the shaft and the coupling. But in this class, our focus is on the electromagnetic design. So that is how we dimension each of these components, the size of it, the shape of it, and the way that we lay out our coils, the way that we select our materials, and so on. We are strictly focused with these active components. So let's now talk about the stator. All right, so the stator, as drawn here, this is a single lamination of the stator. The stator has Q slots. So in this case, if I count this up, I say that we have 1, 2, 3, 4, 5, 6. This is a 6-slot stator. So it has Q equal to 6. So it has 6 slots and 6 teeth. And these slots are responsible for holding the coils, and the teeth are responsible for carrying the magnetic field. And so inside of these slots, we will locate coils that we wrap around the stator. So if we've got a conductor in our hand and we're going to start winding this, we'd wrap it down into this slot. So now it's going down into the page. And we can't see it, but at the bottom of the machine, the other end of the machine, the coil would wrap around over here, and then it would come up out here. Actually, it's probably best to show this as the coil would wrap around down back behind the teeth and connect over here, and then it's going to come up in this slot and go back through, and it would complete this circle some number of times. We call that number ZQ. We say it has ZQ turns. And then finally it comes back up out here and we have a connection. So our coil, if we inject a current, we would have it take this path that we've indicated here with this arrow, and that would be one coil of a phase. Now somewhere else in the machine, we may locate another coil and repeat this same thing. This coil would also have some connection here on the other side of the page, and the connection would wrap around, and you'd complete this ZQ turns again. And if this is a phase winding, you're going to connect these coils in series. So let's move this. Each coil has ZQ turns, and a phase will consist of some number of coils connected either in series or they can be in parallel. And so ultimately, after you've connected all your coils in your phase, you have one final set of terminals, which are your phase terminals, and then inside the machine you have these connections right here going from coil to coil, and these connections are called the end connections. So our slots are responsible for holding our coils, and our teeth are responsible for carrying our magnetic field. And so each tooth will have some specific geometry on the front of it, and this is called the tooth tip. We've got our tooth region here, we've got the tooth tip up here. This back here is referred to as the yoke, the stator yoke, and it is also responsible for conducting field. And during the design process, we need to figure out the dimensions and the shape of each of these components in order to get the performance that we want for our electric machine. So that's part of our responsibility as a designer, to figure out, well, how many slots and teeth do we need? What should Q be? And then once we figured out Q, we need to figure out what coil sides belong in which slot. So in slot 1, are you putting coil sides for phase U, or phase W, or phase V? And then we need to figure out how many turns a coil should have. So that's the number ZQ. And we need to determine the thickness and the shape of the tooth tips, the tooth, the yoke, and so on. So when we say we're designing a machine, that is part of what we are figuring out, is what the shape and value of these different dimensions should be. So stator has Q slots and teeth that hold coils and carry the field, and the stator steel is typically laminated. And so this means that if you were to look at this stack as a 3D profile, so if you take these laminations, this right here would be a lamination, what you'd see is a bunch of laminations that are stacked up on top of each other like this. And the point of doing this is that if you make these laminations thin enough, you prevent eddy currents from forming in the steel region. And if you did not laminate and you just had solid steel, you'd have very large eddy currents that would be induced in a way that opposed changes to the magnetic field. And that causes two problems. The first problem is that it can create a lot of losses. And the second problem is that by opposing the changes of your magnetic field, you actually suppress your motor's ability to create torque. So you have basically a heater. You're left with like an induction heater. You create a lot of losses in the machine and you do not create much torque. And to get around this, we laminate the steel. These laminations can be cut out using a laser cutter, for example, or in large quantities they're actually stamped out. So that's the stator. Next, let's talk about the rotor. And for the rotor, we actually have many options. And the pathway that you pick on this, I'm going to sketch several different lamination and rotor shapes down below. And depending on the type of rotor that you select, it determines the type of machine that you have, whether it's an induction machine, or a wound rotor synchronous generator, or a synchronous reluctance machine, or a permanent magnet machine. So you have the same general type of stator for all these machines, but your rotor structure determines the type of motor that you end up getting. The first rotor option that I'm going to sketch looks like an inside-out stator. That is, it has slots and teeth, but it's inside out because the rotor is inside the stator. So this is a not very good sketch of this, but I think you can imagine what I mean, or you can look it up in your book or in Google. And this is called a wound rotor or a cage rotor. And in this case, these are our rotor slots, and here are our rotor teeth. And actually, what distinguishes this between being a wound rotor or a cage rotor is what you put in those slots. So if you wrap a winding in there, if you wind it with individual conductors that form coils, then it is a wound rotor. And that could be either an induction motor or it could be a wound rotor synchronous generator. If you, instead of putting individual conductors in there, if you fill it with copper or aluminum, it becomes a cage rotor. And a cage rotor, the 3D cross-section looks something like this. So you put your bars through those slots, and then on either end, you connect all the bars together in parallel using rings. So this is actually called a squirrel cage rotor, or just a cage rotor, and it looks something like this. And so each of these lines that I'm drawing down would fill one of the rotor slots. These are bars, and this continues all the way around, and this is what is used in conventional induction motors. The rotating field of the stator induces a current in these rotor bars that is then used to create torque. And so what we sketched up above would be one rotor lamination. The next type of rotor that I'm going to sketch is a salient pole rotor with a field winding on it. And this is used in salient pole synchronous generators. They're really large machines that are used for energy generation on the power grid. So this is a rotor lamination again, and if I can sketch on here a coil that gets wound on here. And this coil carries a DC current so as to create a magnetic field that looks like this. It looks like an electromagnet, where you've got a south pole down below and a north pole up above. And so this is a salient pole rotor, and as I've drawn it, it has two poles. That means it has a north pole and a south pole. And in this class, we denote the number of poles by talking about pole pairs with the letter P. So in this case, P equals 1 because it's one pole pair. You have a pair of north and south poles. Next, I'm going to draw the conventional surface-mounted permanent magnet rotor. And so this design consists of a simple rotor lamination, which is this hollow cylinder in the center, and then mounted to it, glued to it, are permanent magnets. As I've drawn it, it has 4 poles, so P is equal to 2 pole pairs. And you can see that based on the arrows that I've labeled here. So this, on the top of the rotor, there is a magnet with an arrow facing upwards, so that means you see a north pole on the top. To the right, we see an arrow facing inwards, which is a south pole, then a north pole, and a south pole. So there's 4 of them, or there's 2 pairs of poles. And in this structure, at high speeds, you have a challenge as to how to retain your magnets. So as your rotor speed increases more and more, you have greater centrifugal forces acting on your magnets. And so what you do is you put a retaining sleeve on outside of the magnets. And this retaining sleeve can be carbon fiber. You might wind it on there. It may also be Inconel or titanium. And it uses a combination of a press fit with strong hoop strength, that strong circumferential strength, to retain the magnets onto the laminations as you increase the rotor speed. The magnets themselves are typically either, in high performance motor systems, they're going to be neodymium iron boron or samarium cobalt. So these are the rare earth ultra strong magnets. Or in lower cost, lower performance motor systems, they may be a ceramic magnet or a ferrite magnet. Okay, so that's a surface mount permanent magnet motor. There's also an interior permanent magnet motor, which we'll now sketch. And in this case, your lamination consists of a little bit more complicated of a shape. Embedded within it, you have permanent magnets. So again, these are typically rare earth, neodymium or samarium cobalt. But you also have these holes, which are flux barriers. The whole purpose of this motor is to introduce saliency, to make it so that your inductance, as seen by the coils, changes as you rotate your rotor. And so you introduce magnets inside the steel as well as flux barriers inside the steel, so that you shape the path that your field takes to kind of force this change of inductance with the rotor position. The shape I've drawn here is just one of many different interior permanent magnet rotor shapes. The interior permanent magnet motor is very common for electric vehicles or hybrid electric vehicles where you want to be able to operate in flux weakening mode or constant power mode. And so this shape of rotor structure makes it very easy for you to weaken the flux seen by your permanent magnets using your stator coils. And it commonly goes by the acronym of IPM. As I've drawn it here, this is a 2-pole structure. Okay, the final shape of rotor that I want to sketch for you is called a reluctance rotor. So we've been talking about in these diagrams so far using current or permanent magnets to create magnetic field that's used for torque. And then we've also hinted at that you can choose to design your rotor to have saliency. So we had 2 shapes that have saliency. One is the salient pole rotor, and the other is this interior permanent magnet motor, this IPM rotor. And saliency means that your inductance for your stator coils changes as you rotate your rotor, that you have different D and Q axis inductances. The final rotor shape, the reluctance rotor, has no permanent magnets and no coils on the rotor and relies purely on saliency in order to create torque. And this can be used to create 2 types of motors. The synchronous reluctance motor, which can be designed as a 3-phase synchronous motor, or the switched reluctance motor. Okay, so we've introduced the different shapes of rotor structures and talked about how that defines the type of motor that you are making. So all your motors may have the same general form of a stator, but based on the type of rotor that you install in them, they become fundamentally different types of machines, from induction machines to wound rotor synchronous generators to permanent magnet machines and synchronous or switched reluctance machines. And again, these are the active components. The dimensions of these rotor laminations, rotor permanent magnets, rotor coils, stator laminations, stator coils, and so on are the dimensions that we will be designing in this course. The final topic for us to discuss in this video today is analysis versus design, and how this fits into the narrative of our course. So, what does it mean to analyze an electric machine? Well, suppose somebody gives you this geometry. They've given you an electric motor. From how this is drawn, it's a permanent magnet surface mount motor with a 6-slot stator. And if you are doing analysis, you're going to take this defined set of geometry. You're then going to either use analytic calculations, so you're going to use equations, or you're going to use a finite element analysis tool, and we'll talk about that in a later lecture, to calculate your fields everywhere in the cross-section of this machine, your magnetic fields. And from that, you're going to determine the machine performance. So you're going to analyze the machine to determine its magnetic fields and then its machine performance from the magnetic fields. And performance may mean the torque density, or the torque that the machine produces, the losses, or its efficiency. It could mean the amount of torque ripple your machine has. It might be something equivalent circuit-based, such as the power factor or the reactances. But somehow you're going to use analysis tools to take a defined set of geometry and determine how the machine performs. So that's analysis. And that is what your coursework has so far trained you to do very effectively. Your engineering curriculum trained you to take a set of input parameters for a system and determine how that system behaves. That's our conventional mindset. In this class, we're going to be talking about design. And what does design mean? Well, it means that somebody has given you a specified performance. Instead of giving you this cross-section of a machine, instead of giving you this, they just told you, hey, we need a motor that's going to spin 3,000 RPM and have an efficiency greater than 95% and have a power rating of 10 kilowatt. Give us a motor. So you're given a performance specification and perhaps design constraints. Maybe your customer tells you that they want all this great performance, but the motor had better cost less than $20. Give us a design that will work. So you're supposed to take this performance specification and design constraints and come up with a geometry or a motor design that meets this specification. And we can say that this is an inverse problem. It's an inverse because you're given your end destination and you're being asked how to get there. And think back to your linear algebra days. Finding the inverse of a set of equations is hard. Finding the inverse of this abstract problem is very hard. Oftentimes our design specification is under-constrained. We're told that we need to meet a certain efficiency and we need to rotate at a certain speed, but there are infinite possibilities of designs that could meet that criteria. So how on earth do we come up with a single design to propose back to our customer? So we can say that inherently by its very nature, this is a hard task. And when we try to come up with this motor design, we're always left with a lingering question of how do you know if your design is best? And of course, in order to answer that question, you need to start with some agreement on what it means for a design to be best. And that's a trickier question than you might at first think. So how are we going to address this in this class? Well, before we can go to design, we have to build up a set of tools to do the analysis. So the first portion of the class is going to focus on building up a set of analysis tools. That is, building up these tools. How do we calculate the fields in the cross-section of our machine? And how do we convert from our fields calculations to the actual performance of our machine? And fields analysis means solving Maxwell's equations. And once we've built up a suitable set of analysis tools, then we'll be able to talk more about design. And we'll take a two-pronged approach to design. We'll look at coming up with dimensioning and sizing approaches based on analytic equations. And this will be used as kind of a crude first pass at what our machine should look like in order to meet a design spec. We take these equations that we will derive from first principles. This is a very first principles oriented class. We should know where everything comes from. So we'll take our understanding of physics and our understanding of the machines that we have in front of us, and we'll use that understanding to establish design relationships to come up with crude approximations for the different dimensions of our machine. And a reoccurring theme in this class is going to be the wisdom that's entailed in making appropriate assumptions. If we don't make any simplifying assumptions, then it's simply too complicated. Maxwell's equations are too difficult to solve analytically, and we're left unable to make any kind of design decisions. But if we oversimplify, then we're left with highly inaccurate design decisions that simply don't yield workable designs. So we'll be talking about that throughout the course. And that's our dimensioning and sizing approach. And then we're going to also be talking about design optimization using finite element analysis, so that we have accurate estimates of how our machine performs. And we'll get into the theory of optimal designs, Pareto plots, sensitivity analysis, this type of thing. Although our interest is not in the science or the mathematics of optimization, that's an entire topic area, research area in and of itself. We are just going to be customers of optimization algorithms. We're going to spend all of our effort on understanding the machine physics and how to optimize the machine physics, but very little of our effort on actually the numerics of optimization algorithms. So in summary, this video has set the stage for the machine class. We've talked about the components of an electric motor. We've gone in depth on what it means to be an active component of an electric motor and how that factors into the design process. We've discussed both stator motor geometry and rotor geometry and how that defines the different types of motors you may need to work with. And then we've set the narrative for the broader portion of this class, how we'll first be focusing on constructing a set of analysis tools and later transition to using those analysis tools within the design of our electric machine. And this is meant to be a big picture type of lecture, and later lectures will delve into the details of these individual components.